So as Tom said, I'm Zach from the team in Israel. SATLA is the space group based in the kinematic and computational geometry lab in Israel, in Ariel University. I'll be talking today about the SATLA group, the units that we launched so far, and the one that we integrated this week, and hopefully launching in May. Okay, so I'll start. Okay. Sorry. Yeah. So the SATLA project. We've launched until now 2 units. The first one was a 1U called SATLA 1. It had an LED, a LoRa module, and a Raspberry Pi payload, which was the camera. And we also launched the SATLA 2B, which is a 2P unit, which is in orbit from January. Soon we're hoping to launch the SATLA 2I, which is also a 2P unit based on the SATLA 2B that we used. And we are hoping that the community will like the idea and embrace it. We're going to do the SATLA 0, which is going open source with our hardware and software. Our entire schematics and code will be available to each and everyone who wants it soon enough. And our next idea will be doing SATLA 3, which will be a 2 or 3P unit where we will implement the code and the ideas received by the open source community and some other projects. Okay. Yeah. So the SATLA 1. It was a 1U unit launched through the ISS. It had a LoRa 433 UHF module and a LoRa 2.4 gigahertz S-band. It had a single reaction wheel, 2 Raspberry Pi Zeros, each with 8 megapixel camera running OpenCV and Python, an LED array that should have been visible via a 5-inch telescope, GPS, IMU, and TOF ranging. It seems to have an antenna malfunction, thus we didn't have any communication with the satellite after it's launched. Here you can see the photos of the 1U unit that we had and the integration part. SATLA 2B. The entire project, SATLA in general, and also the 2B and 1 and 2P units are made by students solely. No industry involved. All the people working on the projects are bachelor's, master's, or PhD students in the university. So the SATLA 2B is a 2P unit launched on January 22 with Alba Orbital, our great friends. And we are taking a ground stationless approach. This means in Ariel University, we do have a ground station, but we are not using it to pick up the satellite because in Israel we have a huge RF noise floor, so we have no chance of picking it up. We're using a community called Tiny Ground Station, which I'm going to expand on in later slides. Okay. The SATLA 2B is a cost-effective platform for pocket cubes. In contrary to a lot of projects, our entire cost is looking at about $1,000 per unit. Also, we are going to be offering kits, ones of only the hardware and ones assembled. And we will be offering them at cost price around $1,000. Everyone who is interested will be open to buy it if he wants. Okay, so the main controller, we used the TNZ Duino 3.6, which was a very big success energy consumption-wise. We saw that the satellite from the receiving telemetry, we see that it doesn't drop from 4 volts voltage. It's always almost 90% full capacity. And we used LoRa 433 UHF and the LoRa 2.4 S-band. And one problem with the SATLA 2B that it was that the Raspberry Pi is partially not working. We didn't get new images, and the ADCS module wasn't working. So you can see here the mechanical structure of the Satla 2B, the parts, and how it looks from inside. And in the next slide, you could see the entire parts laid out. Also, we have an iFixit article where you can see the entire assembly of the satellite from start to finish with explanation for each steps and up-close images if you'd like to build one yourself, and also a full assembly video where you can also see more of the parts being implemented. So if anyone is interested, you can check it out. There's all the explanation and images regarding the assembly. Here's the power schematics of the Satla 2B unit and also the Satla 2I, which is an improvement unit of the Satla 2B. We're using 4 solar panels with Schottky diodes and a power management unit, babysitter, the main board, and 2 external 8350 lithium-ion batteries, which are redundant, and the brushless motor PCB that holds the ADCS unit. Okay, so as I said, we are taking a ground station-less approach. What it means? It means we're using a community called Tiny Ground Station, which is an open source network of ground stations distributed around the world to receive and operate LoRa satellites. This means that at any point you can get to this link regarding a Satla 2B and see all the data that it is transmitting at each time of the day. We get about 80 beacons a day, and you can see the entire data filtered out and the payload and everything. And you can also, in regard, you can send out beacons to the Satla 2B if you're interested and get your responses. And also what we found with the Satla 2B earlier this year, we saw from the data that we received that we captured a geomagnetic storm that occurred on March 4th and 15th after a moderated solar flare blasted out the sun's atmosphere. You can see it here plotted out in the magnetic field. It occurred about just the same. We can see it in the data as the dates mentioned. This is one of the products that we received from the Satla 2B. So the Satla 2I is our latest unit that we integrated this week with Alba Orbital. You can see the subsystems laid out. We are due to launch at May 23rd. The main controller will be a TNZ 4.1, which is a little power hungry than the 3.6, but we hopefully manage that. And we have an IMU and more sensors on board. And LED array, same as the Satla 2B, that we hopefully be visible enough from a good telescope. An ADCS unit composed of motors and a magnet that is the opposite polarity of the Earth, so it will be drawn to it. A GPS unit, a LoRa UHF unit, and a LoRa S-band unit. In the energy, we're using 2 lithium-ion batteries, as said before, a charger, a BMS, and 4 solar panels. The payload. This time, we're hoping that everything will be okay with the Raspberry Pi. We're using 0.2 instead of the original 0 that we used before. We did preparations for a laser communication stabilization system, free space optics, and we're doing photography and image analysis using the Raspberry Pi 2.0 and an 8-megapixel camera running OpenCV and Python, where we're hoping to get good images of the Earth and some stars and find constellations in the stars and stuff like that. Okay, so what we're using to deliver the images. As we know, LoRa can send packets up to 50 bytes, which is not ideal for sending images. So we're using an approach that is called Laplacian pyramids where we take an image that is usually VGA size, which is 640 by 480, that takes up about 50 kilobytes, which is 10 to the power of 3 packets. We use the Laplacian pyramids to separate the frequencies of the image and compress each frequency separately in order to achieve a better compression rate. We saw that we can get a result of an overall size of 3 kilobytes, which is 60 packets, where most of the layers weighted less than 1 kilobyte. We're using this approach. So if we get a good image that we see from the metadata that we get received from the satellite, that there's an image that interests us and we want to take it, instead of waste a lot of time and send the entire image, we're sending it layer by layer, and each layer we decide if we want to continue and take another layer and see if the image is getting better and it's what we want. We stitch each layer one on top of the other and get a better image each step. So the project goal and vision. We're hoping then that with this unit we can do a proof of concept with the AD-HOC system and see that we can get good pointing with our laser and LED array, and thus create a laser comm link from a satellite, hopefully in one of our next units. The benefits are that it's secure, it's fast, we don't need license band. It requires a lot of ground stations. This is why we also approving of and loving the idea of ground station-less approach and having the help of the community, helping one another. It requires a GNSS, an ADCS, and a sub-1 milliradian dynamic tracing and pointing. Also, it requires a laser comm ground station with a robotic telescope. How exactly are we going to achieve that? What we're doing this time is set satellite optical alignment, which is going to enable the satellite to go to ground laser communication. We need to align the satellite to the ground station. Thus, we can use the ground station to flash a light strobe at the satellite at a constant frequency. The satellite will open a video link, search for blinking light at the agreed upon frequency, and align accordingly. We're using, due to the computing power limitations of the Raspberry Pi, we're using the satellite will not run FFT on the image, but instead sampled images at twice the frequency, which is a Nyquist-Shannon sampling theorem. By the way, the entire code for the satellite optical alignment and the Laplacian pyramids can be found at the GitHub link, which is mentioned here. I know you probably can't see it, but anyone interested, I will send it over after. So our team. Currently, a lot of people worked on the SATLA project in the past. In the SATLA 2i, currently we are a dedicated team of 5 people. Boaz Ben Moshe, who's the head of the computer science department in Ariel University. Oni Ronen, which is a PhD student for computer science. Michael Bitrin, which is a master's student for electrical engineering. Myself. And Asaf Haya, which is also an electrical engineering student. To sum it up, SATLA, we're hoping to create a place and move a movement that people will take the open source community also for our hardware and also for the software, and try to make an example for other people to open up their ideas also to the world and push the research forward by sharing knowledge and capabilities. And I hope you like the idea and consider it. Thank you for your time.